Why are we here? What's the origin of life? Why the properties of the universe are the way it is still a quest.
The 30-meter telescope will allow us to understand each and every one of these questions.
The primary mirror is 30 meters across. So that's 3 times the diameter of the current largest telescopes.
At that scale, it's virtually impossible to build a single piece of glass. So the way we will achieve this size is through segments.
TMT builds on the heritage of the Keck Observatory. The Keck telescope was the first segmented mirror. The mirror itself is made up of 36 segments that all lock together to make a single surface.
30 meters is roughly 400 segments. It's big enough that you can make the next leap in terms of our understanding of the physical universe, while not being so big as to be unbuildable.
We have chosen the summit of Mauna Kea as the site for the 30-meter telescope. This followed a 5-year campaign of testing sites all around the world. It is an isolated mountain in the Pacific Ocean, has extraordinarily good atmospheric turbulence properties. This gives us very sharp views of the distant universe. There's been great progress over the last 10 years in a phenomenon which we call adaptive optics, which allows us to correct for the blurring in the Earth's atmosphere.
The trick to this is to shine a laser into the atmosphere and to watch the spot to tell us how that atmospheric distortion is happening.
So the correction effectively takes out the twinkling of starlight and renders them as very sharp points of light. It means we not only can see fainter objects, but we can actually see details much more clearly than we would ever have been able to before. The Hubble Space Telescope has definitely set a milestone in high-resolution imaging. We've all seen beautiful pictures of distant galaxies. TMT, with adaptive optics, gives us a much finer quality of detail than Hubble Space Telescope. Hubble is about 2.5 meters across. TMT is 30 meters across. So we have that ratio, a factor of 15 or so, improvement in image quality, plus the bigger aperture that enable us to see fainter details. So you're impressed with Hubble? Wait till you see TMT. When we look deep in space, we're looking back in time. And so what I'm trying to do is, in a sense, build a picture book of how the universe has evolved from its beginnings to the present day. The 30-meter telescope will allow us for the first time to understand when did the very first galaxies and stars switch on in the universe.
The big challenges in astronomy is to be able to detect Earth-like planets around stars other than the Sun. And this to date has not been possible. And with the 30-meter telescope, we should be able to detect an Earth-like planet and to take spectroscopy of this planet to understand the potential for life elsewhere in the universe.
90% of the material in the universe is dark. We don't see it. The 30-meter telescope will allow us to look at the structure of dark matter. If you like, its granularity. Is it smooth? Is it lumpy? On very, very fine scales. TMT, in studying dark matter, will actually complement laboratory experiments trying to detect dark matter, for example, at the Large Hadron Collider in Geneva. So TMT is an enormously powerful science instrument that's part of the armory of the physical scientist over a wide range of wavelengths and even disciplines. It's 400 years since the telescope first was invented, and it's been an astonishing story of scientific discovery. And the 30-meter telescope will extend and continue that story in a dramatic way.